Hello everyone, and welcome to our next installment of the SaferSim webinar series. So today we have a presentation from researchers from Puerto Rico-Mayaguez. I will mention we do have a chat box in the bottom right-hand corner of your Adobe Connect window. If you do have questions or comments, please type those in that chat box. We will have time at the end of the presentation to address those questions. And now I'd like to welcome our first presenter. We do have a few today, and our first presenter is Dr. Didier Valdes. And I will turn it over to you, Didier.
Thank you very much, Jacob. First of all, I hope that everyone is staying safe and healthy. Welcome to our webinar. We will be presenting today the results of our SaferSim project entitled Enhancing School Zone Safety, Case Study in Puerto Rico Using Driving Simulation. At UPRM, we work collaboratively in our projects. Our research team includes professors and graduate research assistants that participated in this project, as you can see here. Our webinar today includes short presentations from each one of the professors at UPRM involved in this project. I am Didier Valdes, and you will hear also from Benjamin Colucci and Alberto Figueroa. Our webinar starts with an introduction to our research problems and objectives, then the main tasks developed in this project that includes an online survey and the 2 driving simulator experiments. That will lead us to our main conclusions and recommendations. Let's start. According to our highway safety data, pedestrian deaths amount to a high proportion of fatalities in our highway systems. Let's see some numbers. Looking at the information related to pedestrian fatalities in our highways, they have increased by 35% between 2008 and 2017. Also, in 2018, almost 6,300 pedestrians died, which is the largest number since 1990 in the US. Puerto Rico is among the 10 jurisdictions with the highest pedestrian fatalities. In 2018, almost 37% of the total road fatalities in Puerto Rico were pedestrians. Besides, the statistics show that there is a significant safety problem in school zones. McKay and other researchers reported in 2016 that there were 5 teenage pedestrian fatalities every week in the US. In this project, we studied school zones that are locations with significant interaction between drivers and pedestrians, with issues related to the possibility of distracted children crossing the street and drivers speeding along the school zones. In the literature, we found several factors that are related to pedestrians' severe injuries and fatalities. In our study, we explored the case of uncontrolled mid-block crossings. According to NHTSA, in 2017, more than 50% of the pedestrian fatalities were related to drivers' failure to yield to right-of-way and improper crossings of roadways. As we all know, an uncontrolled mid-block crossing is a potentially dangerous situation for both pedestrians and drivers, where the time that the pedestrian needs to cross the roadway safely is weighted against their perception of the approaching vehicle speed. Therefore, the data related to pedestrian safety highlight the need for innovative approaches to eliminate pedestrian injuries and fatalities in our highway system. Now, the 2 main objectives of our project are, first, to evaluate the effectiveness of enhanced traffic control devices on reducing speeding behavior and increasing speed limit compliance, and second, to study the behavior of drivers when they encounter a conflict with a pedestrian at an uncontrolled mid-block crossing. Our methodology included the typical task on a research study, from literature review to conclusions and recommendations. 2 tasks that I want to highlight in our methodology are online survey and the 2 driving simulator experiments. Dr. Benjamin Colucci will talk now about the online survey and the first simulation experiment. Dr. Colucci.
Thank you very much. Thank you very much, Dr. Valdes. In terms of the web-based survey, it was conducted with an online instrument that includes 23 questions divided into the following 6 sections, namely demographic information, school transportation characteristics, speed perception, understanding of school zone signage according to the MUTCD, and the presence of traffic control devices for speed control as well as for warning pedestrian presence. A total of 306 participants answered the web-based survey, with roughly 60% female and 40% male, representing 3 age groups, namely 18 to 25, 26 to 40, and 41 to 75, with the corresponding percentage distribution found in this slide. Next one. In terms of the level of knowledge, as part of this web survey, the level of knowledge of the participants with regard to school zone signs was evaluated. The participants' response for the 3 signs is summarized in the table. The response corresponding to the pedestrian crosswalk sign designated in MUTCD as W11-2 was 98.5%, while the knowledge of the school zone sign, that's the designation S1-1, and the school crosswalk sign, that's the other designation S1-1 W16-7P, with the black arrow below the sign, corresponds to 48.9 and 43.9 respectively. In the next slide, we show the stated preferences of school zone TCD combinations. The stated sequential preference for the 4 school zone traffic control devices combinations are shown on the right-hand side. As you can see, start from the top, the vehicle going passing those 4 sequential zones. Essentially, what we see is that the relative frequency of desirable responses, combination C was 87.4% and combination A is 57.5%. In both TCD combinations that included the overhead sign with the flashing beacon as the preferred ones for the participants. Next one. Next one, please. Let's go now into the simulation study of the first case. This is the UPRN driving simulator. That is essentially a driving cockpit simulator with a driver's seat, a steering wheel, gear shift, acceleration, brake pedals, and turn signals, complemented with a visual display that is 3 fixed projectors, 120-degree screen visibility, and 1080 pixels in terms of resolution. The computer system is a non-motion driving and audio system. In our first case study that we're covering is associated with the secondary unit Samuel Adams School. That school the main access is through Highway PR2, that is a 4-lane high-speed divided arterial that is part of Puerto Rico's national highway system. It's under the Puerto Rico Department of Education and teach students from pre-kinder to 9th grade with an enrollment of approximately 900 students. The annual average daily traffic is 35,000 vehicles per day. The posted speed limit is 45 miles per hour and the designated school zone limit is 25 miles an hour. 3 representative photographs that you can see on the right-hand side as a result of the observational studies that were conducted in the study area and taken from a pedestrian bridge crossing Highway PRT are shown on this slide. The upper left photograph on the left-hand side illustrates the inbound traffic approaching the school entrance, parked vehicles in the right-hand side shoulder, and adult pedestrian in the sidewalk. The right-hand side photograph shows vehicular traffic, parked vehicles in the right-hand shoulder, and the presence of pedestrians, both adults and children. Vehicular traffic approaching the school zone initially observes vehicles parked in the right-hand side of the shoulder, parallel to the traffic flow. As the traffic approaches the main entrance of the school, there's an increase in the shoulder width, and vehicles tend to park in diagonal fashion, 45 degrees to 80 degrees, both in reverse and in up front, and even some are parked on top of the longitudinal solid white edge line between the shoulder and the driving lane. A concrete median with a cyclone fence separates traffic from each direction, and representative single-unit trucks that travel through this highway are also illustrated in the lower photograph, roughly representing 8 to 9% of the traffic. Next one. In terms of the experimental design that was used in this project, it consisted of factorial design with 2 configurations, the existing or current configuration with the traffic control devices in place in Highway PR2 and the proposed configuration with the enhanced traffic control device following the design specifications of the FAWA manual on uniform traffic control devices, having that corresponding flashing beacon and overhead sign. The three independent variables that were evaluated are the presence of pedestrians, vehicles parked on the shoulder, and the presence of vehicular traffic in Highway PR2. The three dependent variables that were evaluated in this experiment are lane position, mean speed in miles per hour, and acceleration noise. A total of 36 subjects participated in this research study with essentially 50-50 split in male and female drivers, representing three age groups, in this case is 18 to 25, 26 to 45, and 46 to 70. Next one. In this particular slide, you can see a plan view of the 16 and proposed configuration, illustrating the different zones of interest and the traffic control devices in the Spanish language that were used in the school zone. Also, you can see as part of the simulation, there is on the lower part, you can see that if an inattentive pedestrian walks unexpectedly toward traffic lanes on zone 3 in scenarios with parked vehicles in the shoulder. In zone 1, you can see in the configuration 2, the proposed signage for the school zone, and in the zone 2, you can see our proposed signage in Spanish with the overhead sign with 25 miles an hour and flashing beacons. Next one. In terms of the representative results that we got from the study, this slide shows the mean speed difference between configurations in miles per hour between configurations in the 12 scenarios that were evaluated for the 4 zones of interest. The main finding is a reduction in mean speed in 70.8% of the scenario zone combinations. Please also note in the table the positive values that represent speed reduction observed in the proposed TCDs associated with configuration number 2, that is the proposed configuration. Next one. There were speed profiles developed for all the 12 scenarios, and here we're showing one representative one, that is a scenario number 10, that corresponds with the presence of children only, does not include adults, vehicles parked on the right-hand shoulder of Highway PR2 adjacent to Samuel Adams Elementary School, and no traffic flow was present on front. That means they were flowing from free flow condition, and the traffic was moving from left to right on the upper part is the configuration 1 that is existing, and configuration 2 that they proposed, and you can see the different zones of interest. Next one. And the last one in this section of the first case study, another pertinent finding was the increasing compliance of the school zone speed limit in zone 3 in percentage. From the table, you can see the 12 scenarios, and you can see configuration 1 and configuration 2 showing zone 0 and zone 3, and the compliance, which is the difference on both in percentage. Essentially, the increase in compliance with school zone speed limit was in the range between 5.6% and 27.8%, and the red values that are shown in these cells represent a higher speed compliance observed in the proposed TCD scenario configuration number 2. Now the next presentation goes to Dr. Alberto Figueroa that presents the second case study. Thank you very much.
Great, thank you. Welcome everybody. The second site we studied was the Franklin D. Roosevelt in the city of Mayagüez. The access to this elementary school is through a side street that is parallel to the arterial highway PR2, the same highway we talked in the previous school. But in this case, on the left side of the school, there is a signalized intersection and the access to the side street. Another entrance from PR2 is located on the right side of the school. This time, the PR2 highway has 6 lanes with more than double the AADT than for the Samuel Adams School described earlier. The speed limit is 40 miles per hour, but the observed 85th percentile in this location was 53 miles per hour. Adjacent to the school, there are 2 residential areas and a government center not pictured that generates significant pedestrian traffic along the corridor. Even though there is a pedestrian bridge at mid-block, this bridge is not ADA accessible. Therefore, pedestrian crossing the PR2 roadway at mid-block is very common because they will not or cannot use the bridge and are not willing to walk up to the signalized intersection. This experiment included 6 scenarios with 2 independent variables. One, the time of day, and second, the pedestrian crossing direction. 2 configurations were used as similar as the previous experiment, one with existing traffic control devices and another with enhanced traffic control devices. The order of the scenarios were assigned randomly for each driver. The experiment was conducted using 12 different drivers for each configuration. That totals 24. The gender was divided 50-50, and we had subjects from 18 to 68 years old. The enhanced traffic control device that we used was an overhead warning sign with flashing beacons, similar to the previous one, but in this case with a different text that says there is no school zone along this segment, but we have the safety issue with pedestrians walking along the segment and crossing Pier 2. So the text, cruce de peatones adelante, translate to English as pedestrian crossing ahead. The objective was to evaluate if the enhanced traffic control device helps in reducing the number of pedestrian vehicle conflicts at the Pier 2 segment. Let's watch a video of a simulation scenario with the existing traffic control device. The driver started at the shoulder and was free to select any of the travel 3 lanes. The only information provided to the driver was the speed limit and to drive straight along Pier 2. Notice the shoulder on the right side and the sidewalk is located on the left side. There is also a horizontal curve to the right before reaching the school. One detail I didn't mention was that this scenario included the pedestrian crossing from the right to the left of the roadway, coming from the side street, like simulating a pedestrian that didn't use the pedestrian bridge. The driver was not told about the presence of that pedestrian crossing the roadway. This experiment was designed to create a potential conflict between the driver and the pedestrian crossing the road. The pedestrian was programmed to not react to the presence of the vehicle and walking at a constant speed of 6 feet per second. 3 zones were used to analyze the driver behavior. Zone 1 was a position where the driver was assumed to drive at free flow speed well before the overhead sign. Zone 2 was located after the overhead sign, so the driver was already warned about the possibility of pedestrians on the roadway. At this zone, the pedestrian was still not visible to driver. And Zone 3 was the conflict zone, used to detect the reaction of the driver to the presence of the pedestrian. So let's see some of the results. In this case, we see the speed profiles obtained for the scenario 2. That's for daylight conditions and the pedestrian crossing from the left to the right. Remember, configuration 2 included the overhead warning sign. The speed profile goes from the right to the left, so we can also see on the profiles a vertical line on the right that represents the location of the overhead sign. The second vertical line on the left of the graphs represents the location of the pedestrian crossing the road. So you can see that the speed profile had significant difference in terms of mean speed and speed dispersion between scenarios 1 and 2. Another interesting finding from the speed profile was that half of the drivers reduced their speed by 25 miles per hour when facing the pedestrian on configuration 2, compared to only 25% of drivers that reduced their speed in configuration 1 without the enhanced traffic control device. So we went further and studied the conflict between the driver and the pedestrian, and we evaluated a zone 250 meters long prior to the pedestrian path. The left graph represents the position of the vehicle and the pedestrian. In this scenario, the pedestrian was crossing from the right shoulder to the median. Each point on the graph represents the positions at 1 second intervals. The dashed lines represent the center line of each travel lane. On the right graph, we can see the vehicle speed at each position. So at point 0, the driver is traveling on the middle lane close to 60 miles per hour. Point 0, the pedestrian starts to walk from the side street toward Pier 2, but is not yet visible to the driver. 5 seconds later, at point 5, the pedestrian is inside the right lane, and the driver is still going on the middle lane at a speed of around 60 miles per hour. Please notice that the driver starts to brake after point 5 to avoid hitting the pedestrian. 2 seconds later, at point 7, the pedestrian is reaching the center line of the middle lane, and the driver has reduced his speed to 45 miles per hour and started to change to the right lane to avoid hitting the pedestrian. With this type of analysis, next one, we analyze conflicts from points 0 and 5 to evaluate if the overhead sign had an impact on the number of conflicts. The results show that the scenarios with the overhead sign were associated with a lower percentage of conflicts on 6 of the 8 locations analyzed. On the right side, you can see a graph that shows the avoidance maneuvers selected by drivers when facing the conflict with the pedestrian. Almost half of the drivers decided to brake when facing the pedestrian. The percentage of braking-only events was lower on the scenarios with the overhead sign. Lane change with or without speed changes were less selected by drivers, even though the scenario didn't have ambient traffic. So this decision raised the flag that the decision to brake could have a negative consequence of rear-end crashes under light traffic conditions. The last analysis we performed in this case was a model that we calibrated to identify factors that define the chance of a driver facing the conflict with the pedestrian. Overall, 3 factors were found to be significant. The model indicates that the pedestrian crossing direction, TCD, from left to right increases almost 4 times the chance of having a conflict with the pedestrian. Notice that the road has a horizontal curve to the right, so the driver eyesight could be fixated on the white pavement marking on the right side to follow the road geometry without noticing the pedestrian coming from the left side or the other direction. The model also confirms the positive safety effect of the overhead sign. The results confirm the overhead sign with flashing beacons decreases by 65% the chance of a conflict by making drivers more aware and alert of the presence of pedestrians crossing the road. So with that, I'll leave to Dr. Valdes to finish the presentation.
In terms of conclusions, I'm only going to highlight a couple of aspects that we found in the online survey and the 2 simulation studies. From the survey, one of the major conclusions is that half of our drivers lack understanding of fundamental meaning of the school zone sign and the school crosswalk sign. From our school zone experiment, it was found that by providing information in a clear and more visible way, it is possible to reduce speeding and crash severity. Our proposed traffic control device configuration showed a reduction in mean speed and also higher compliance with school zone speed limits. From our mid-block crossing simulation study, one conclusion is that the proposed enhanced overhead warning sign was effective in alerting drivers of the presence of pedestrians crossing the roadway. We also found that braking was the driver's main response in 86% of the cases when they were in conflict with the pedestrians in the mid-block crossing. In addition, the direction in which the pedestrian was crossing was found as one of the significant factors for the driver's reaction. We understand that these findings contribute to the discussion in the transition from partial to full automation in the autonomous vehicles development worldwide. Based on the simulation results, it's recommended to apply innovative signage to improve safety in school zones and also continue further studies on vehicle-pedestrian interactions. We understand that the topic of vehicle-pedestrian interactions is of special concern for ongoing automated vehicle research. We would also recommend to expand the current virtual simulation research on pedestrian gap acceptance to include multi-lane arterial streets. We would like to thank SaferSim and the University Transportation Centers program of the U.S. Department of Transportation and all the extraordinary people listed here that help us complete this project. Now, if any of the participants in the webinar has questions, I will be glad to take them or one of my co-presenters. Thank you very much for your.
Thank you, Didier, Ben, and Alberto. As Didier mentioned, we do have a few minutes for any questions or comments. There is a chat box here at the bottom right of your window. So if you do have any comments or questions, feel free to type those in now. And we do have a note from Dawn Marshall, the Safer Sim director, for the nice presentation, and I will echo that. So thank you all for the interesting work that you're doing in Puerto Rico. We have a couple other participants typing stuff in. I will mention that this presentation will be uploaded online to our Safer Sim website and YouTube page, and that should be online by the end of the week if you do need to go back and re-listen to anything. Oh, and that is our next question. Is the presentation going to be uploaded and where can it be accessed? So it will be uploaded, like I said, to our website and our YouTube channel. Since you have registered, we will also send that link directly to the registrants. So if you have registered, you'll get that right away once it's available. Okay. Well, I'm not seeing any questions. I think that might be due to the excellent presentation, like we've said from all of you guys. So, if you do have a final thought or concern, you can reach out to them, Didier, Ben, or Alberto. Their information is online. But with that, I will turn it over to you, Didier, for maybe a final thought before we close this meeting.
Thank you very much, Jacob. Just to mention that the final report is also available in the Safer Sim website, and we have a couple of papers that have been also presented at the TRB and other conferences. So feel free to reach out if you think that our information can be of help to you. Thank you very much, Jacob.
Great, thank you, Didier. And I will actually mention on top of that, so when we do send out the recording, we will also send a link to that final report. So it'll be a direct link there if you want some more details on that. So with that, I will end this meeting. We will be having our next webinar. It's from the University of Iowa, and that will be on Tuesday, May 12th at the usual time. So you will be seeing information about that here soon. Thanks again for the presenters, and thanks for everyone for joining.